that. And thank you everybody for attending. Much appreciated that you're joining us this afternoon. What better way to beat the heat than sit inside like we've been doing for 3 months and talk about data science. You know, we're not a huge crowd, so I think we can be a little bit more interactive, and you don't have to listen to me talk the whole time. So we'll go through and talk about different things. So yes, I am Jay Meil. I'm a senior principal data scientist with SAIC, and I want to take a minute to give kudos to CL because he is the president of HugoNet, and he is the one who found me and helped me secure this job with SAIC. And a few of you on here I know are also working with CL at placing you in data science jobs, cleared or non-cleared, throughout the government space. He is a great resource. He's very smart, he's very humble, and he is persistent. If he believes in you, he will help you win. So thanks again, CL, I appreciate that.
You're welcome. Thank you, Jason.
So I got all these crazy titles. You know, CL told me to beat my chest. I'm not going to beat my chest. What I want to focus on here is I have no special talent. I am only passionately curious. That's my favorite quote from Albert Einstein. I've done a lot of certifications and a lot of courses on Coursera with IBM and MIT and College of London and Harvard and Wharton and things like that, but it's all things that you all can do as well. I strongly advise everybody who's getting into data science, go look at the resources out there, especially if you're already coding. The resources are endless. There are so many great things on edX and Coursera, and then of course HugoNet and their AWS series and their courses that they're doing to help prepare you for the job market. I'm going to focus on AWS today, but just to frame, I know a little bit about Azure and a little bit about GCP. I haven't worked much with either, but some of the places that I'm working have adopted one over the other. I think the first thing I will say is if you're going to be working in the government space, the most important thing you want to do is be cloud agnostic as much as possible. So you want to be sure that you have a good, you know, everybody needs to know AWS because that's the buzzword, but you need to make sure that you understand, you know, if the S3 space in AWS maps to Azure Blob in, you know, Microsoft Azure. So those are just some things to keep in mind. We're also going to be talking about a couple systems today that are real, living, breathing systems that are already in place. Things that my team, who most of them are a lot smarter than me, helped build and framework build and put into production in the government. And we are using what we're doing as a use case for DHS and for a few other government agencies. So I will just get started. So what are we really talking about? Any of us who are working with big data, whether you're an engineer or data scientist or even a software developer, we have a big data problem. It's like, why is it a problem that we have big data? I mean, that's a good thing, right? Well, we're heading into this era of big data computing, and I wanted to sort of give you a little scope and scale here. So just to imagine for a second, because I'm very visual, I can't wrap my head around, you know, big numbers and things like that necessarily. So if you pretend for a minute that 1 byte of data is equal to the size of planet Earth, and I'll just for fun, I'll throw this out there. Can anybody imagine how much data we are generating in terms of, you know, of size? We'll stick to our solar system in terms of size every day. Anyone want to try and answer that? If Earth is 1 byte, how much data are we generating every day? Okay, I wouldn't want to take a crack at it either. We're generating the equivalent of 2.5 of our suns every day in data. So if you think about how big the sun is, I don't know how many amateur astronomers we have. I don't know the size of our sun exactly, but I know it's huge. And we're generating here on planet Earth 2.5 times, or 2.5 the size of that every day. Data is growing at an exponential pace. I heard a really crazy fact the other day that 95%, yes, I know some of us are statisticians and we know that 80% of statistics are made up on the spot, but I really did hear this and verified it. 95% of the entire data in the world's history has been generated over the past 2 years. So we have a lot of data. This is like the new gold rush or the new oil rush. The global data sphere, right? How much data we have sitting today, and obviously it grows by some magnitude, order of magnitude every day. But today, or actually to be fair, I think this was last year. So last year, according to IBM, the global data sphere was approximately 18 zettabytes. Whoa, what's a zettabyte, right? Like, we're not even talking about those very often. Sometimes we talk about petabytes or exabytes, but so again, I had to wrap my head around this. Well, 1 zettabyte is the equivalent volume of data that is equivalent to the amount of water in the Pacific Ocean. So our global data sphere is 18 zettabytes of data, and that was last year. We have a ton of data, and 90% of this data is dark. And what do I mean by dark? I mean that it is unstructured, unlabeled, unstructured, untagged, dirty, duplicative, dark, inconsistent across sources, fragmented, disparate, whatever you want to call it. Those of you that work with it know it, especially in companies and governments. That's what it's like. Whether it's capture or exhaust data, 90% of this data is unstructured. So we, as data engineers and data scientists and people in the data space, and we're here to sift through the mess, right? And not only just sift through the mess, but we have to come up with a performant way and an optimized way to sift through this data ocean, literally, and turn it into something. And what do I mean by something? So I'm not a data scientist by background. My background was finance and fintech, and I spent a lot of time in economics and econometrics and mathematics. It was only a couple years ago that I got into data science. But what I found out is I've really been doing data science since before there was data science, because I've been doing statistics and mathematics and inference from data. That's all I did. I read charts and did inference. I did my own personal machine learning inside my own head. So over this 16, 17 years, I've realized, especially in finance, but actually this is applicable everywhere, is first of all, data delayed is data denied. I tell this to my government customers all the time, no matter what department I'm working with. If we can't get the data in real time or near real time, it's not worth it. Think about it like the stock market. Forget about the government for a second. You ever tried to trade with delayed quotes? 20 minutes delayed, 5 minutes delayed, 10 minutes delayed. Your orders are being filled and the price is already blown by you one way or the other. So that's my first axiom. Second is big data computing algorithms live and die by the data that they're fed. Okay, that ties right back into the first one. If it's delayed data, it's garbage in, garbage out, right? So what's our job? Our job is to take data. And what is data? I mean, data itself is just string. If we're talking in terms of software engineering, it's strings, integers, floats, modulos, binary. It's noise. There may be some information in there. There's artifact, and that's it. And then they dump that big data ocean there for us. So we use a process that I'm going to walk you through today, and this is what I'm going to share with you. And we leverage AWS and some other tools to take data to what I tell my customers is actionable intelligence for their mission. So like I said, data is noise, information, and artifact. Data filtered and processed or transformed becomes information. Still not good enough. Information given context is knowledge. And we believe knowledge given application to the subject matter expertise becomes intelligence. And that's really the job of all of us data scientists or business analysts or data storytellers, whatever you want to call us, is to go from that raw 90% of junk and make inference out of it. And of course, we want to automate that as much as we possibly can. So breaking the 80-20 rule, optimizing the optimization. I felt so clever that I came up with that. 80% of our job as data scientists, as you all know, is not the sexy model building and analysis and training computers and trying to recognize cats and dogs, or in the case of my team, SpongeBob characters for one of our single shot detectors. That's a small part of it, right? Most of what we spend our time doing is playing in the sandbox with data, mining, wrangling, formatting, cleaning, scaling, decomposing, transforming, selecting features, variables, and then we get to play with models every once in a while. So like anything else, it'd be really cool if we could automate as much as possible of that data preparation and the ingestion phase, right? So that we can spend more time building models and doing analysis and sort of having fun with the data. So how do we optimize that? Well, we're all architects, right? We come up with a system. And as my data engineer put it, who works on my team, an amazing guy, it's really three problems. It's master data management, it's analytics, ML, DL, and of course now the new buzzword RPA, for those of you who don't know, robotics process automation, which I have to say I'll talk about a little bit. I'm gonna go down a little rabbit hole for a second. I'm working on a project right now for a three-letter agency in the government, and we were showing them a similar solution to what I'm going to show you today. And they said, what about RPA? We want an RPA center of excellence. And maybe it's my technical arrogance showing, or maybe it's I just didn't want to go learn something new. I thought to myself, why are we doing macros on steroids? Because that's what RPA felt like to me. I didn't really have a choice. I had to figure out RPA and how to phase it in. And so I met with some great people at UiPath and talked to some people at some other companies. And I found that really RPA is a lot more than just macros on steroids. It is a great way to phase in different systems, and it can do a lot of really cool stuff. So if I had time, I'd go back and I'd say, fine, we'll throw RPA in there with analytics, machine learning, and deep learning. By the way, you guys notice I'm not using the word AI. I personally am on a mission to break that from my stakeholders, my customers, and the people that I work with. Yes, machine learning and deep learning, and even some analytics and RPA are all parts of the whole AI system. But I don't like to use the term AI because I think then we're talking sentient beings and things like that, and we're not there yet when, our precision and recall on a binary classifier between a cat and a dog, isn't even at 100%, right? So machines aren't going to take over the world yet. So I try to use what it is, whether it's machine learning or deep learning. Where the new word I'm hearing now is it's machine learning, and then you have shallow learning and deep learning, or whatever you want to call it. You guys know what it is. So master data management, this analytics and machine inference or machine intelligence piece, and then DevOps. DevOps is where I'm weakest. I will tell you that right now. I have an incredible DevOps lead on my team. And any of you who are putting together teams, or any of you who are joining teams, you have to have a very good DevOps person to help stand up your models and get them moving. Although, again, down that RPA rabbit hole, RPA has some ways that it can actually host models for you, so you don't have to do API endpoints, you don't have to do microservices and things like that. So there are some ways around it. But you want to have a really great DevOps person. I'm lucky to have that on my team, and a really good data engineer as well. So what does that give you? That gives you the ultimate. That's like the data science unicorn, right? you got the trifecta. That's how you build a team that takes data and turns it into actionable intelligence and does it in a way that the data is not delayed, right? So we all talk about that, but we don't really think about how it's three problems, at least I think. So we're going to talk about this, what I've titled a unified data analytics and machine intelligent framework. Woo! I love that. We came up with that. So we all know big data is, you know, what is it? It's like 3 V's, then it was 5 V's, and it was 7 V's, and at some point it's going to be N V's for data. But thinking of like volume, velocity, variety, value, whatever you want to call it. You have to you understand that there's a lot of data that's going to be coming into your system, and you have to be able to capture whether it's batch or stream. But you need a system that I think does these 5 things, and we've kind of proven this out over the past 12 months. Our team has made a ton of mistakes, and we've come up with something that's really good. And I'll give you these 5 key takeaways. You need an ecosystem or a framework, or whatever you want to call it, a workflow that's modular, meaning you can piecemeal and take it apart, put it together, whatever you have to do. You can change something, it's not going to affect the rest, which is very similar to what they're doing in software development now. It's not monolithic, right? Everything's sort of a microservice structure. So you want your data space to be modular. You need it to be scalable, because inevitably the government and or private industry is going to need to ingest more data at some point. So it needs to be scalable. It needs to be reproducible. You know, that whole part I was talking about, that whole 80%, it would be really great if we can reproduce as much of that as possible. It needs to be extensible, meaning it can grow. So for example, this particular model that we're going to talk about, it's extensible. A customer says, hey, we want to see RPA added into this. Great, we're going to add it into it. And oh, by the way, we're going to add a feedback loop so that RPA uses something called, or at least with UiPath, uses something called AI Fabric. And now we don't have RPA anymore. We have IPA, not the beer, but intelligent process automation. So instead of just bots that are by very strict rules and bounds and guidelines, you now have bots that are making intelligent decisions and doing the repeatable tasks that humans are doing. And finally, testable. It's got to be testable. And in data science, I often wonder where a tester comes in, because, you know, we're doing a lot of testing and our experimenting and research and development and everything. But I have found that having a tester is very important, especially when we get to the integration stage, right? Integration testing is huge, especially when you're sometimes dealing with systems that don't play nice in the sandbox. And we all know that we have disparate data that we work with, but we also work with disparate systems that weren't really designed to talk to each other. Okay, so master data management. I started to talk about this, right? Volume, velocity, volatility, veracity, variety, whatever you want to call it. They keep adding a V to this, you know, every week. But if we look at big data as like a pyramid, I would say volume is the base. And we just talked about the volume. We have 18 Pacific Oceans worth of data out there, right? Velocity, you need information to flow quickly. That goes back to my whole data delayed is data denied. Stock market data, it's got to move, man. Any of the data, banking data, everything's got to move. Can't be slow. We got to have good data pipelines and good ways to move this data from point A to point B in a very timely manner. Variety. That was one I think that was part of the original 3 V's. So people always talk about big data. Well, if you're only working with, you know, integers or strings or something like that, even if you have a couple petabytes of it, like logs, for example, one of the agencies I'm working with, we're doing some log analysis, and we have petabytes of log data. Well, that's not technically considered big data because it needs to be different sources, right? So we're talking different types of intelligence. So it could be visual, it could be files, it could be real-time streaming, it could be batch, it could be binary, it could be anything. The point is there's a variety. Veracity. This one, okay, it's the equivalent to quality, right? Is it clean? Is it accurate? We need to make sure it is, because like I said, our models live and die by the data. And then value, because if we sit here and build models, we all know that we can have a blast, just, comparing different, single shot detectors versus, a faster RCNN, or what's going to give us the least latency for the best inference and all that. And we get all excited about all that stuff. But in the end, it's our stakeholders, either in the government or commercially, they have to be able to use this stuff, right? There has to be a point to it, not just us playing in sandboxes, as fun as that is. So we need to have accurate results or accurate inference, and we need to be reporting accuracy. We have to have consistency with our data and our results. We have to be able to validate it. There's my timely word again, so important, especially in the national security space or the financial space. And accessibility. And accessibility is probably the most important, I think. And what I mean by accessibility is we're dealing with stakeholders and end users who are likely low code or no code oriented. And they need access to their data, and they need it now, and they need it to be right, but they also don't want to have to do any SQL queries or do any coding or anything like that. And they need good dashboarding is what I would call that. So like I said, we're going to go through the whole process that we're using. So we're going to start with ingestion. We choose, and I'm a super huge supporter of, in fact, I think they should be giving me more than swag, but I'm a super huge supporter of Databricks. And we'll talk about the different systems in a minute in terms of running big data processing. But Delta Lake has a partnership with Databricks, although Delta Lake just got picked up by the Linux Foundation. And Delta Lake is a fancy word for a Delta encoded data lake. Whew. All right, what is it? So first of all, this is where the master data management problem gets solved. You can convert your Oracle Parquet files or JSONs or whatever into Delta encoded format. And what does that do? That gives you ACID transactions. And for those of you who don't know what that is, don't feel bad. I didn't really know either. And I always screw up this word, it's atomicity, consistency, isolation, and durability. And what is that? Okay, great. So what does that really mean? What it means is you have consistent transactions, you have anonymous transactions, you have isolated transactions, you have fault tolerant transactions with your data moving back and forth. Something else that's nice about the Delta Lake format is your data can be either unstructured, semi-structured, or structured data. So it's gonna ingest it batch or stream, it'll ingest all of it, right? And then all these others, it's scalable, it unifies into other systems. There's schema enforcement on read or write. And it also has a cool feature of essentially time travel where you can go back and forth. Now, where does it sit in the AWS space? Essentially, all it is it's like a layer, if you think of like a layer, on top of an S3 bucket or multiple S3 buckets. Or again, if you're being cloud agnostic, on top of blob storage or cloud storage, depending on who you're working with. The real beauty behind Delta Lake is that it has scalable metadata handling. So it leverages Spark. It was designed for Spark, and it leverages the disputed processing power and can handle metadata ingestion and data ingestion at exabyte scale tables with billions of files at ease. And again, it's streaming and batch unification, which I started to talk about. So it's a streaming source and a sink, if you want to call it. And then, of course, it has this data versioning and enables rollbacks. So here's how we used it. You'll notice in the center of this blue box, there's three, they talk about these three sets of tables. You can call them bronze, silver, gold, or we call them bronze, silver, gold, platinum, or ingestion, refined, feature aggregated. But here's the idea. It's abstracting away the data engineering portion from the data scientist, which is really nice because you have data engineers working on it. So what do I mean by that? I'll give you an example. One of the ecosystems that we work in has let's see, a little over 1,000 tables, and probably within all those tables, there's probably 80 or 90 million rows of data, right? So do we need all that? No, we work from about 30 or 40 tables that are updated in incremental load, and we don't need all those rows. So you can decide what you're going to bring in, and this becomes your ingestion layer. This is where you do all your really big transformations. So your big merges, your joins, your group bys, all that stuff. And then you set this data into, we'll call it a layer of the Delta Lake. And then your data scientists can hit that, and it's the data that they need, and it's not the data that they don't need. And it's already cleaned for the most part. Then we can move to a refine label, or a refine layer, or table, or whatever you want to call it. The data science pull the data, and then they start playing with it. You start cleaning it. You start, figuring out what you need and what you don't need. You drop your nulls. You do all your data exploration, your exploratory data analysis, and now you save those tables here at the refine table level or the silver level. And then you start getting into model building. And, let's say you're doing feature selection, or you've done PCA, or, some type of dimensionality reduction algorithm or something like that. You don't want to have to do it again. Remember, this is all about speed and being able to replicate what you've done. Now you have an aggregated data store where you can set up these areas to do multiple experiments. So an example is when we were trying to figure out for one of the image capture tools that we were creating, we were trying to figure out what was going to be the best type of neural network to use. We were able to tap the same table and run 10 different experiments at the same time, distributed across Spark clusters, and training and providing inference, and then sort of aggregate all of that because we had these repeatable or reproducible layers set up. So Delta Lake is a very cool feature of Databricks. It is open source, and I believe you can get it outside of Databricks. And again, I think it's going to be spread more soon because it's been picked up by Linux Foundation.
So Jay, does it support only relational data, RDBMS?
It is an RDBMS. Well, first of all, it's not an RDBMS, but it does support only relational data. It's not really designed for graph data. Does that answer that question?
Yeah, and then the NoSQL. I don't know about the NoSQL.
Yeah, it'll do NoSQL to a degree. Delta Lake's good at what it does, and it's really not good at what it can't do. So the other thing it's really not good for is a lot of people sort of use Databricks and Delta Lake incorrectly, and they use it as just like a SQL querying engine, as opposed to like going directly to Oracle or directly to RMDBS, and it's slow for something like that. That's really not what it's designed for.
Okay, good to know.
Yeah, that's a good question. Does anyone else have any questions on Delta Lake? Okay, so that's the ingestion piece. So let's talk big data frameworks for a second. We've all heard of Hadoop, the elephant, probably heard of Hive, metadata store, Storm, Spark, and Flink. Maybe not a lot of people have heard of Flink. So what's the difference between these? They all run on HDFS. They all run on the Hadoop file system. But what's the difference? And I set out to understand the difference because I really wanted to know, because Spark's the most used. It's what we see the most. But they're all distributed computing clusters. Obviously, Hadoop does MapReduce. Everything else does compute in memory and all that, which MapReduce doesn't do. But Hadoop was designed for batch data, okay? And then Storm was designed for streaming data. So that's what they do really well. Hadoop does batch, Storm does streaming. Spark was designed to do batch and streaming with an emphasis on batch. And Flink was designed to do batch and streaming with an emphasis on streaming. So if you ever wanted to know the differences, those are the differences. I threw that in there because everybody hears about Spark, and sometimes you hear about the other things in the Hadoop ecosystem, but you don't really hear about Flink very often. I don't know if does anyone know anyone using Flink? I've never played with it. I don't know much about it. But again, we're going to be talking about Apache Spark in the form of Databricks. So Apache Spark, everybody knows, distributed computing program, interactive processing, real-time stream handling, batch handling, in-memory processing. It makes things go very, very, very fast. If there's anyone on here who's not super technical, think about it, the old Christmas lights versus the new Christmas lights, serial processing versus parallel processing. Or think about it in terms of, if you're a dev, in terms of like computer CPUs, right? Like single thread versus multi-thread. It has the capacity to speed everything up. It has, on top of that is Databricks. So Apache Spark was developed at Berkeley and it's open source. And then the guys who created Spark went and created Databricks, which is getting a huge momentum in the government and the commercial space because it's got multiple language support. It's very fast. It has advanced analytics. It's general purpose. It's cloud agnostic. It's got a pretty decent framework. And for data scientists, most of its interactivity is inside of notebooks. You know, similar to Jupyter notebooks, but they're Spark notebooks. So they're fault tolerant and they're distributable. So they're called RDD notebooks, resilient distributed data set notebooks. But it's essentially, it's a Jupyter notebook. And you can switch between languages. So you can switch with just very simple magic commands. You can switch between Python. You can switch to SQL. You can switch to like a command line interface. You can switch to Scala if you so desire. And it's very fast. So I'm a huge proponent of Databricks. So what does Databricks really do? All right, and I realize that this is a Linux penguin, but I really thought this was fun to put a daemon up here, right? So the Spark daemon, I put this in two ways. I did it in standard clusters and high concurrency clusters, but I really did it so if people like to read left to right, or if people want to look top down, they can look at the workflow or the schema either way. Spark has a driver, right, with a Spark context that's connected to the RDD notebook. It has a cluster manager, and then it has workers, which have executors and a cache, and it's done in memory, and they can execute tasks as needed. Excuse me, I'm just gonna grab a drink real quick. Does anyone have any questions while I grab a drink? I'll grab a drink. So Spark allows applications, if you're comparing it to Hadoop, for example, like MapReduce or EMR or something like that, Spark runs about 100 times faster on the basic level. That's not even if you polish up your clusters and do cluster management things and policies and all that stuff. But it's about 100 times faster. It's a powerful open source framework, and it's probably its most important feature, although not so much anymore because cloud storage is so cheap and it's really just sitting in an S3 layer also, is the in-memory cluster computing, which is responsible for increasing the speed, and it's definitely an alternative to MapReduce. It's a low latency cluster computing system, so we've talked about this whole data delay, data denied thing, seeing sort of a theme here. And it's for very large data sets. I've asked for this latest project that we're going to be working on, what's going to slow Spark down, and I've been told so far that it can ingest, it can stream ingest petabytes and even exabytes. So I haven't seen it myself yet, but it sounds like that doesn't surprise me that it can do that. So let's talk about how this like driver and memory works, and I get a little bit more technical for a minute. So the driver memory is controlled by what they call the Spark driver memory, and in the default configuration. And like I said, the default configuration is 100 times faster than MapReduce, and MapReduce is of course a lot faster than other ways to do it. From there, you have your cluster managers and your master nodes. And then it distributes out to your workers. You can scale however you want. I'll give you another example from what we're doing right now on our machine, on our one of our image classifiers. Sorry, I'm making sure that I say things correctly, so I'm not breaching any type of rules. We were running it on, we were testing it, we were doing integration testing. I talked about the importance of testing. We were testing it on a microservice that was built in the system that's going to touch it, and we were running 96 nodes essentially, and we could have scaled all the way up to 960 if we wanted to. We could go higher than that, but we were blowing out their microservice every time because it couldn't keep up with how fast inference was being made with Spark. And that's because of the high concurrency clusters. The high concurrency cluster is a managed cloud resource. The benefit is you have Apache Spark, it's native, it's fine grained, and it shares maximum resource utilization and minimum query latencies. And here's how it does it. It does two things. It has something called preemption, which proactively preempts Spark tasks from overcommitting. So it will scale automatically. It actually has a load balancer and an autoscaler that will scale up and scale down your clusters as necessary. And then also it's fault tolerant. So if one of your cluster goes down, think back to the Christmas light example, if one of the clusters go down like a Christmas bulb, not everything goes down. Everything's running concurrently and is parallelized. So that's pretty cool. The most important thing I think Spark does, or I'm sorry, Databricks, because that's, we're talking about it. The Spark's the engine, Databricks is a sports car, is resource allocation. So I started to talk about that. The idea is it will help allocate the amount of data, the time the job has to complete, whether it's going to be this dynamic allocation of resources, and where it's going to do upstream or downstream changes. Spark does it, or Databricks does it, and does it all. So let me see if I can get a laser pointer on here, and I'm not sure whether I can. Let's see. No, I guess I'm just gonna spotlight. Does that work? Okay. No, I'm gonna say no because it's asking.
You can use the cursor. The cursor
Is
is
it
okay. If you point the cursor, that's enough.
Okay, you can see on the cursor. All right, great. So from the driver node, it connects to the cluster manager, right? And this is generally a Hive metastore where it's touching to. And the cluster manager allocates the resources across the applications, and the managers communicate with each other. The Spark acquires the executors on the nodes, right? And the applications get their own nodes, and you can scale up and scale down as many nodes that you need, and tasks are sent back and forth by the Spark context to the executors. The number of executors and their memory settings play a major role in the Spark job. If you run executors with too much memory, then you get excessive garbage. You have to really kind of figure out how to optimize the Spark job. That's one thing that's more of like the art, right? It's more of like a touch type thing, and I've got some guys who are a lot better than me at doing that. So that's if you do static allocation. You can also do a dynamic allocation where it's automatically using that load balancer and the cluster optimizer. Everything is picked up based on the requirements. So size of data, amount of compute needed, and then it releases it after use. And that allows, remember we talked about reproducible, it allows those nodes to move on to different jobs. If it's done, it clears its cache, it moves on to the next job. So you can select your number of cores, you select your number of executors, you select your number of nodes, you can select memory for each executor. There's a whole bunch that you can configure on Spark on yourself, or you could do that whole dynamic allocation that I mentioned. Any questions on this? It's a lot to talk about.
No, the diagram on the right hand side is just the expansion of the one on the left with more colors. Is that how it is? Or?
It's an expansion of the one on the left with extra tasks, so it becomes a high concurrency. It's the representation of a high concurrency cluster, and so high concurrency clusters are a little bit different. in how they work. It's a managed, I think I mentioned it's a managed cloud resource, but standard clusters are normally used for a single user. I think that's the big takeaway. And you can run workloads in what you need to. And then high concurrency clusters you want to use in like a data science team. So for example, we're running 4 Databricks shards, and within those shards, we're running multiple clusters on cluster management because we have a data engineering area that's doing all of our data ingestion and transformation. We have a staging area where we're doing like integration testing and things like that. We obviously have production, which is holding our productionized models and running inference, real-time inference or, asynchronous responses to different microservices or APIs that are hitting us. And then we also have our development area. So if we didn't have these high concurrency clusters, plus we have 14 guys working on it sometimes at the same time. So these high concurrency clusters prevent failures and prevent blowouts from, running out of memory and things like that. So it's not really, I think you're right. It's not really well documented, but it's supposed to show that there's in the high concurrency ones, you're seeing like an order of magnitude of 3 more executors, and let's call it an order of magnitude of 10 of each of the tasks.
Right. So the only thing that surprises me in standard clusters, you can see workers can talk between themselves, but in the high concurrency, they are not shown to be talking between themselves.
Yes, that is correct, and that has to do with, and I'm not that technically savvy with this part of it, but it has to do with fault isolation and preventing. They can communicate with each other, but they communicate with each other through the cluster manager. So it's almost like if you've done high performance computing and you've ever used like MPI, like a message passing interface, it's passing back and forth through the cluster manager and they can communicate with each other that way. I think it's not so much that the worker nodes are communicating with each other as the tasks that they're being done are communicating back and forth with the caching. So it's going faster each pass, essentially.
Right. So we can configure according to the requirement. Okay, that's fine.
Yeah, you can definitely configure it according to the requirements.
Okay. Thanks.
Sure. Let's see, I talked about controlling the number of executors dynamically. That's, load, it's task dependent. What's cool about, I think about all the cloud technologies now. I mean, Kubernetes does this, and EC2 instances do this, and that's one of the really nice things is it scales up and scales down as you need it, right, automatically. But the thing about Spark jobs is they come in all shapes and sizes and cluster form factors, and you can literally go from the tens of nodes to the tens of thousands of nodes and executors, or seconds and hours to even days for job duration. Or like we talked about, something small like megabytes all the way up to exabytes of data, and simple EDA, right? Or sometimes, again, it's a little bit latent, but use simple SQL queries, all the way up to complicated analytical workloads and deep learning. You throw in streaming into that, you've got batch and machine learning jobs. You can see, right, the infrastructure of why Spark and Databricks become so fantastic. And I haven't even shared with you the machine learning side of that yet. So we'll talk about that. We'll talk about that next. Here's one more way to look at it. Again, it's resource allocation. I got ahead of myself, but you have your Spark core, and then on top of that, you have your Spark SQL and data frames, which is your RDDs. You have MLlib, which we'll talk about in a little bit. There is GraphX, which is a component you were asking, like a NoSQL component. It's not great. Those of you who work with graph databases, Node, it escapes me now. Node.js, is that what it's called? Node.js is probably better, and it has a Spark connector to it, and then Spark streaming. You can also visualize what your clusters are doing. using using DAGs, and that's kind of cool. We use something called Ganglia, which works really well in Spark. I've heard from other people that it's not that great of a tool, but it seems to interface well with Spark. But one of the biggest problems that any big data processing job has is data skew. It's one of the most common problems, and the graphs can show the skew across the data set. It can also show it by partition of the data. It can show it in the key value space. It can identify skewed stages. You can do a skew deep dive. You can see per partition runtimes. You can analyze joins and things like that for potential issues and see that join inputs are different in size, like, I don't know, 65 gigabytes versus, like, 1 gigabyte or something like that. If it's doing, that. And when jobs fail, or nodes fail, or workers fail, which happens sometimes, you are able to see, you get fantastic visibility into when and where failures happen, how Spark responds to them, and was there any collateral damage, which really there shouldn't be, right? Any collateral damage, because it's fault tolerant. So again, Spark's 100 times faster in memory than Hadoop. It's about 10 times faster on input output in the disk. It can sort 100 terabytes of data 3 to 6 times faster. And it's because of its ability to use DAGs and the bounds and the ability to parallelize what it's doing, whatever job it's doing, whether it's analytics or whether it's ingestion or anything like that. So talk about real quickly MLlib. So we've talked about data ingestion. We've talked about data processing through Spark. So now let's talk about RDD-based machine learning, essentially. And MLlib is Spark's scalable machine learning library. It has a lot of common, we'll call them white box learning algorithms. So compare it to your like scikit-learn and Python library. The difference is everything that you can do within this library is distributable across clusters. I understand that scikit-learn is creating a distributable method that you can allow to distribute, that just makes it go faster. It can do a lot of statistics. It does classification and regressions, linear models, support vector machines, log and logistic regression, linear regression, decision trees, random forest, naive Bayes, different type. It does k-means clustering. It'll do single value decomposition, principal component analysis, feature extraction and transformation, and optimization. But it's under active development, and I would have to say it's okay, but it's a little bit of a kludge right now, I think. There's not a lot of support on it. You're probably better off using scikit-learn and doing a single node build. And if you were doing something where you were looking more on the black box space and you were going to build like a neural network, I would highly recommend using TensorFlow. The thing about TensorFlow is also, it's vertical, and it's a vertical scale on a single node build. But I told you that Spark is open source, and Databricks is getting a ton of exposure to the government space and to the commercial space. And the guys at Uber developed something called Horovod Runner, which is essentially basically a 3-line function that instantiates a distribution protocol for TensorFlow. So you can actually train in a distributed cluster. So we all like TensorFlow better. Of course, we like TensorFlow 2.0 because it's essentially Python. And it's a little bit more user friendly. And of course, when you're building deep learning tools, there's a lot more that it can do. But I wanted to mention MLlib because it's built in. TensorFlow is also built in, and in fact, the guy from Google who developed TensorFlow has been stolen away and now works for Databricks. So I think there's going to be a lot more integration of TensorFlow or making it even easier to distribute across the clusters in the future.
So Jay,
So,
quick question. I just quickly wanted to know in that square under
yeah.
MLlib, the hypothesis testing chi-square tests,
Yeah.
that rectangle is just standing on its own. Does it have any relevance, like any like down the line with anything?
I think the idea is, I mean, I can only speak for, this is their graphic. I can only speak for what we do. We do a lot of initial statistical testing when we do exploratory data analysis. And if I were interpreting this graph, perhaps what they're trying to say is we're going to hit dead ends sometimes because data science is such an iterative process, right?
Right.
Whether or not that's the true interpretation, I don't know, but that's how I would interpret it. That okay, you get your data, you refine your curate, you find your features, or you find what you think your features are. Then you start exploratory data analysis and start doing maybe you're doing some naive Bayes or some testing there and things like that. You split your data into train test splits, and then this is just showing different pathways that it can go, whether it's a classifier, random forest, an ensemble, logistic regression.
Okay, that name is funny. Chi-square.
Yeah, it's chi-square tests.
Chi-square. Chi-square. Okay.
An old. I mean, it's not old, but it's it's statistics, and it's basically. Let's see, guys, if I can remember this. I don't use it. We actually use mean squared error for most of our testing, but the chi-squared test is a test that. Let's see. So you've heard of p-values? Have you heard of that?
No, not really.
Okay, so
it's okay. I don't want to take everyone's time. Yeah.
That's okay.
Right.
P-values are a way to test your null hypothesis and see if your null hypothesis is verifiable or not. And chi-squared test is just another way to do that. Different hypothesis. And I definitely think that's why there's a dead end there, because it's saying, okay, well, maybe our hypothesis was wrong, so we move on to something else.
Okay, thank you.
Sure. ML flow. Yeah, go ahead.
Before we proceed, can you help us in understanding, you just told us that MLIB is RDB-based ML. Do we have something, which is equivalent for deep learning?
For deep learning, you could use PySpark or TensorFlow. I would use TensorFlow all the way. And we use TensorFlow because it's basically all Python commands. And again, you can use Horovod runner, and with a very little bit of code, 3 or 4 lines of code, you can start running all your deep learning training and testing, validation, everything in a distributed format. Even though TensorFlow is natively a single node vertical build, you can get it to distribute horizontally across with Horovod runner, which is also open source.
And it's all Python, correct?
It's TensorFlow 2 is all Python. TensorFlow, if you're using previous versions, it's a little bit clunky, but it definitely TensorFlow 2 is much better. And I guess it's preference, right? Some people like PySpark, some people like TensorFlow, some people like Keras, some people like MLlib. Some stuff you can just do with scikit-learn, right? I mean, you don't even need it. But that's the idea behind the farthest left side of this ML flow piece, is that it works with everything: XGBoost, TensorFlow, Keras, scikit-learn, PySpark, MLlib, whatever it is you want to do, whatever your flavor is, right? You can run MLflow, which is also developed by Databricks and it is also open source. So we use, so far, just to recap for a second, for data ingestion, we use the Delta Lake model. For data processing and compute power and everything like that, we're using Spark, RDD, things like that. For our model building, we're using primarily TensorFlow and Horovod Runner, and then MLflow, which is what I'm going to talk about now. So the easiest way to explain MLflow is it does three things. It generates model formats that standardize deployment options. It registers your models, centralizes and creates collaborative lifecycle management. And it also containerizes models, which is fantastic. It will create images and put it in do a Docker image for you and set it up so you can go throw it on a Kubernetes pod and be done with it. I guess the easiest way to explain how MLflow works is it's basically a lightweight set of APIs and interfaces that can be used with the entire machine learning workflow inside Databricks. And again, as I said, it has that model and model registry. It can record and query experiments, code, data, configures, results. It also has a time travel, so you can roll back, and you can also compare. So I told you about, like, we did 10 different distributed training jobs and testing jobs with, really, if you think about it, 10, it was more like 50, because we did 10 different models with five-way k-fold cross-validation. So that's like 500 different, if you're thinking about the different combinations, like 500 different ways that it can run. And MLflow keeps track of all of that. And you can then start setting up matrices and correlations and things like that and decide, okay, what's going to be, is it A, is it B, is it C, is it N? What's the best way to do this? In terms of the type of model that you're using. So like we got down to deciding between a faster R CNN or a single shot detector model, and then which variables we were using, and different ways that we did the validation and different ways that we did our actual data tagging and things like that. And just to kind of carry that through, we found that the faster R CNN, if anyone's out looking at doing ODM stuff or OCR stuff, we found the faster R CNN gives you faster inference, gives you more accurate inference, but it has a higher latency. And the single shot detector gives you a little bit lower in terms of your quality of inference, but it has a lot less latency. And we went with the faster R CNN because we knew that for our model, in this case, we were doing batch processing with asynchronous responses, so they weren't going to be instant. They were going to be a couple seconds delayed, and we wanted, because we're looking at pictures of things, we wanted higher percentage precision or inference. So that's MLflow. It sort of helps you organize all of your data stuff, all the stuff that you're doing inside your notebooks, and collaborating. So it's a pretty cool tool that allows you to do all this stuff, from staging all the way through production and archiving, and the best part, obviously, is, at least in my opinion, because I'm not a dev, is the containerization, software image, and then the Docker image. So CI/CD. Go ahead. I'm sorry. What? It is open source. Yes, it's open source. I don't know how you'd run it without Databricks, because it is technically Databricks MLflow, but it is open source. So I'm assuming you can run it on something else. I don't have any experience with that. Okay. So CI/CD with TensorFlow and PyTorch, I guess. We'll use it sometimes. Data science is a funny animal. It's not like software engineering. We're not putting out, necessarily new models every week or new deployments every week. Mostly what we're doing is using feedback loops to make our precision or our accuracy or our recall, whichever one we're focusing on, more intelligent, and making our models more intelligent by feeding back the decisions that it's made into itself. There's really two ways you can go with this. You can use, right now, it's probably not the optimal choice, but it's what the government allows. We have Jenkins, CloudBees, and so technically we're using that for CI/CD, and it's a great tool for CI/CD. But we have a lot of data moving a lot of different places between our train and our build and our tests and our deployment and Docker and Kubernetes and everything like that. So we've been having some talks about whether we want to bring in Apache Airflow. That's not a CI/CD tool, but it's a data movement tool. And right now we're trying to decide, is it faster to move our data from point A to point B, which we're not doing right now? Or is it faster to move code using Jenkins pipelines from point A to point B and then execute that code and call the data to wherever that's going? So like if we're going from, let's say from our dev shard to our stage shard, right now we're using a Jenkins pipeline. We're not actually migrating the data, we're migrating code because Jenkins isn't good at moving data. So we migrate the code to the other thing and we run the job, and then that brings the data in. If we were to do Apache Airflow, again, open source, and of course works great with Spark, it's distributed, it has all the other same qualities of the distributed compute frameworks, we could actually move the data. So we're actually looking into that right now. I don't really consider data science CI/CD, except for the dashboarding and reporting part for the end users. And that's more of the master data management issue than it is, building models and things like that. Again, we make our models smarter. That's continuous integration, continuous delivery. We make our dashboard smarter. That's continuous integration, continuous delivery. And we make our data move faster, right? And we get it in more real time. We've gone from, in 11 months, we've gone from a system that was doing remember I told you about that massive RMDBS data set? That's an Oracle transactional database that there was a read replica for the data science team, and that read replica was getting killed and filled every night. And it was taking 4 to 5 hours, and a lot of times it was breaking and not filling. So you were lucky if you got refreshed data every day. And oh, by the way, they didn't account for different time zones, so they started at a time that didn't make sense. So even if everything worked perfectly, you didn't get all the data you needed. We've gone from that model to leveraging Delta Lake, leveraging Spark and Databricks, and now we have in production an incremental load that takes about 10 minutes to go from the read replica to Spark. Then we can do whatever we need to do, and it takes about 5 minutes to go from Spark to a Tableau server if it's going to be dashboarded. So our clients are going from having completely stale data to about a 10 to 15 minute delay in data analytics, and then maybe depending on how fast we run our batches, a couple minute delay on machine inference for different things that we're doing. And again, to go down that RPA rabbit hole for a second, I have been told that RPA can do some of this stuff that is manual and repetitive and can make some of these things even faster that we're looking at, but I'm really not talking about, RPA today. So that's what we're doing right now in terms of deployment. And that's about as good as I can get on deployment, because that is not my, you don't want me deploying into production, put it that way. I play with models. I don't deploy into production. That's why I said we have a really good DevOps.
This is beautiful. What you shared is beautiful. Yep, it's good. It's good.
Thanks. So let's talk about the whole architecture, right? I redid this. This is not what we're doing, but this is very similar to what we're doing. But CL and his partners asked if I could tie it into, make it look like an AWS type scenario, and I found something. So we talked about what Databricks can do. You can have streaming, that would be coming through AWS Kinesis. You can have batch, which would be coming through AWS 3. Your S3 is going to be fed by things like crawlers, maybe AWS Athena, QuickSight, Redshift. I strongly don't recommend Redshift, but I didn't say that. Redshift's expensive, it's clunky, and ironically, Redshift is supposed to mean getting away from Oracle, but I don't find that it's necessary most of the time. We looked at integrating Redshift and we decided against it. We wanted to use Athena, which is essentially serverless RMDBS. And we're using Athena for some of our metadata stores. AWS Glue, how can I think? AWS Glue is sort of like a schema enforcement tool. So schema on read or schema on write, and basically it helps you ingest your data into Delta Lake and get it into Delta Lake by converting it from like Parquet or JSON or some other file format, YAML, whatever it is, over to Delta encoded. And then of course we talked about the Delta Lake inside Databricks. That's where it's sitting. It's sitting on that S3 bucket or on the Kinesis. We talked about ML flow. We talked about it commuting back and forth between Redshift. And then if you abstract down a level, you have this, these 4 phases. You're sourcing. Again, I took this from AWS, so of course they're going to talk about Redshift. That's very expensive. So you've got your sourcing, and then your phase inside of the, we'll call it the Spark ecosystem, or the machine intelligent ecosystem, is your exploratory data analysis, your model building, your train test validation, logging, tracking, deploying, and then phase 4 is serving models. And of course, Amazon's going to talk about Amazon SageMaker, and they're going to talk about ground truth, and they're going to talk about all these things that they can do and build things for you. SageMaker is not, or was not as of last check, in most cases, FedRAMP moderate, so you can't use it yet. And you definitely can't use ground truth yet. And that's a funny story if anybody ever wants to hear what we did to get around using ground truth. We needed to, this classifier I was talking about that does images, we had untagged images, and we needed to tag 30,000 images. So I should have called the Guinness Book of World Records, because you had a bunch of data scientists running around like monkeys, figuring out how to build our own tagging software, which we built. We stood up a little bit of a tagging program, which is really cool. And then over 7 days, about 6 or 7 of us, because of clearance levels and things like that, tagged 32,000 images twice. So 64,000 image tagging by hand. So like I said, I should have called Guinness Book of World Records. It will probably go down in history as the most expensive tagging job ever, because it was all data scientists doing it. And that's all we did for 7 days. But if Amazon SageMaker gets FedRAMP, one of the cool things about ground truth, which is a sort of a layer on top of SageMaker, is it does transfer learning. And because it does transfer learning, you might only need to tag 500 of those images manually, and then it'll tag the other, 60,000, 63,500 automatically. So you're basically, you're training the model to train the model. And that's pretty cool. The reason it hasn't been approved yet, my understanding, just from talking to like ISSOs and things like that, is nobody likes its workflow. There's like a mechanical Turk workflow to it, and it's on S3, and there's not a really good ICAM policy around it. And if someone pushes the wrong button, you could theoretically release that information out into, into the ether. So they consider it, a security leak. And they still consider it a security leak, even though we use, S3, I didn't really talk about this. I'll talk about this for a minute. S3 obviously can have standard S3 encryption, where it's using an S3 encryption key. It can have SSE KMS, which is server-side encryption key management service, where you have your own unique key, or you can have client-side encryption, where your S3 bucket is communicating with something like OpenShift to encrypt and decrypt on the client side. Some of the agencies I work with keep everything very localized and out of the cloud. Some of the stuff that we work with, we do SSE KMS, no problem, that's good enough. But a lot of what we do, especially with sensitive information, if it were to leak out into that ether or into that sandbox, it's going to be encrypted anyway. It's not going to be readable. It's going to be junk. But of course, everybody has to be safe. So those tools are getting held up. And I hear that a lot of the cool tools that Google has developed, and a lot of the cool tools that Azure has developed, are having the same problem. The other thing is, maybe not so much SageMaker, but some of the other tools with some of the other cloud services, they're more of a low code type thing, or like things like Data Robot are doing. It's more low code, and that's fine. But what we found is low code does not handle unstructured data, and it doesn't handle unsupervised learning. So it's really great to have these systems that you click a couple buttons and you pass in your data and you get all this inference. But we talked about 90% of the data is dirty data, right? Or dark data. And we talked about how most of that data, even after you get it into some structured format, still is not necessary. Your problem still may be unsupervised. And so we find that we use unsupervised learning a lot for exploratory data analysis. We use k-means, k-modes, db-scan. I'm just, throwing different names of algorithms out there, but we'll use that and we'll go from centroids to classes. So in other words, we'll go from an unsupervised model, we'll get the inference off that, and then we'll create a supervised model. And I found that most of those systems are lacking in dealing with the EDA and unsupervised learning and unstructured data. My understanding is same with RPA. Again, it's on my mind right now because I'm presenting something on it next week, but RPA is great when it's within the bounds and it's rules-based and the data is structured and the data is cleaned and the data is tagged. It doesn't work with dark data. So there's a lot of these cool things coming out, but you have to be able to navigate as a data scientist or a data engineer. You have to be able to navigate like working through all these problems and figuring it out. And I will end with this. We said that AI wasn't there yet, right? But I think this cartoon's hilarious. We all hate those reCAPTCHA things. I think the guy who invented reCAPTCHA should be clamshell packaged or something. But to prove you're a human, click on all the photos that show the places you'd run for shelter if the robots had an uprising. thought that was funny.
That's good.
That's what I have, guys. You can ask me questions. I may or may not be able to answer them because of data issues for classification, or just because I'm not smart enough to answer the questions. I'm definitely not the smartest guy out there when it comes to this stuff. This is all still pretty new to me, but I'm learning as fast as I can, and I'm really enjoying what I'm doing. Data science is awesome. Machine learning engineering is awesome, and working with SAIC has been great because they let us do what we do best, which is play in sandboxes. You're not held by bounds. So thank you for letting me talk. I think, man, CL, we did that like right on time. If anyone has any questions, fire away. I'll be here for a little while. So thank you. Appreciate it.